So we're at example 20 here. So we are going to try to find the area of a region bounded by the graph, the x-axis, and two vertical lines. So let's highlight, first of all, let's remind ourselves, area. What do we know about area? Area must be always what kind of a value? Area must be positive. Area must always be positive. So as we draw this thing, if we get any negative spots, we might have to clean those negative spots up. So we're going to try to sketch this function. Oh boy, that's going to be interesting. The x-axis and then these curves, I can deal with that part. But, well, let's give it a whirl. So I'm going to kind of bias my curve towards this because I'm only going between, what's that, 1.5 and 2.25, I think. So wherever that is. All right, this curve is not so easy for me to predict what it's going to look like. So let's talk about the easy parts first. What do we know? We do know where the x-axis is. That makes my life pretty easy. I do know about where 3/2 is, or 1.5. I'm not going to get super detailed in my picture here, but I'm going to draw my boundaries as, say this is 1.5. I'm going to say this is 2.25, okay? So that's this section that we're looking at. But what's the curve doing in there? So what can you tell me at least about the curve as you look at this thing? Well, hopefully you can tell me that the outputs will always be what kind of value? One is positive. I don't care what this is, but whatever it is, when I square root it, it's going to have to be greater than 0. So it's a positive divided by a positive. So my curve is always going to be positive in here. So I don't know what it looks like. I'm going to draw it kind of wavy there. Wavy maybe. Maybe f of x. I don't know. But I don't have to worry about any of that area being negative. So I can just straight up do an integral. Before I get going, though, I should probably check to make sure that this stuff, I do see this makes me a little nervous. So I want to check the domain of this function to make sure that these two values are legal within the domain. So our domain, do we have any problems? Yeah, we've got two problems. We've got the x on the bottom, and we've got an x under the root. So we can handle that all at once. This stuff can't be 0, but it also has to be non-negative. So we can combine that into just saying got to be positive. So 3x minus x squared has to be greater than 0. Well, let's try to make a sketch of this function to see where we've got any issues. So if I factor out an x, that's going to leave behind 3 minus x is greater than 0. What can you tell me? I'm not going to go any further. I don't want to make a sign chart. I want to get a quick sketch and get moving on. I know that this shape, what is this graph going to make? It's going to make a parabola. What are these zeros? We just figured this out when I ZPP this. What are the zeros of this parabola? At 0 and at 3. What kind of parabola is this? Which way is it pointed? It's pointed down. So what are all the values of x that are greater than or equal to 0? Everything, so in other words, if I picked anything outside of 0, all these values are positive, right? If I pick any x value that's smaller than 0, or any x value that's greater than 3, I'm going to get this value to be negative. So my domain of my function, domain of f, lives from 0 not inclusive to 3 not inclusive. Does that work with our 3/2 here and our 9/4 here? Yeah, those fit within. 9/4 is 2 point something. So those both fit in our domain. So we don't have any issues there. So we don't have any problems in our domain. Sorry, we don't have any problems in this interval. So we can just straight up do the integral to calculate the area under the curve. So our area is going to go. So the beginning is from 3/2 until 9/4 of my function 1 over 3x minus x squared dx. Alrighty then. let's see what we can do here. So this doesn't fit with any of my rules from before or my inverse trig rules, because one of those is supposed to be a constant, and I don't have that. Let's try to do that move where we complete the square. Let's see if we can rewrite this as a complete the square problem. So this is going to be 3/2 to 9/4 of 1 over the square root of, and now I'm going to rearrange this so that the x term comes first. Now, if you remember, when you complete the square, this term cannot be negative. It can't be anything other than 1, even if it's -1. So I'm going to go another line down here. One over, and I'm going to factor out that -1. That's going to leave me with x squared minus 3x now, plus blank for my completing this square. Now, if I distribute that negative, this thing would end up being a negative, so I need a plus blank at the end to undo that negative blank. All right, let's complete the square, cut it in half and square it. So if I cut 3 in half, that's what, 3/2? 3/2 squared is 9/4. 9/4 again. So I now have the function, the integrand of 1 over negative x minus 3/2 squared plus 9/4. I don't usually like to write my fractions going slashing, but I'm running out of room there. And then I can rearrange this to get this so it looks like one of those inverse trig function things. (9/4) minus the quantity x minus 3/2 squared dx. And now all of a sudden we can start to define who is who here, who is u and who is a, because this is the square root of, that's a squared and that's a squared. So if you hopefully have it memorized, I always have to look it up because I'm not taking the AP test. So I'm looking for the one that has constant minus a function under a root. Constant minus a function, that's the arc sine world. So I'm going to be doing this according to arc sine. I do have to look at what u and a are, though. So a would have to be the square root of this, which would be 3/2. U is x minus 3/2. That's the thing that's getting squared there. And then when I find du, that's just dx. So life is good. I don't have to worry about I don't have to try to find any, what do we call them? Corrections. I don't have to make any corrections. So let's integrate this thing. So this is going to turn out to be, I'm going to go way over here, try to give myself a little bit more room. So this turns out to be the integral of, according to arc sine, I got to look it up again. It's arc sine of u over a plus c. Arc sine of u, which is x minus 3/2, over a, which is 3/2, plus c. No, I don't need the plus c because this is a definite integral. So this integral is going from 3/2 until 9/4. So now we can evaluate this integral. So that means I can put 9/4 in here. That's going to be arc sine of, 9/4 minus 3/2. I'm going to turn that into 6/4. So that would end up being 9/4 minus 6/4 is 3/4. But that's still getting divided by 3/2. So I'm going to have to flip and multiply that in a minute. Minus, and I'm going to put 3, I like that. 3/2 minus 3/2, that's 0. So I don't care what you're dividing by as long as it's not 0. So that's going to be arc sine of 0. I'm going to flip and multiply, so I would get arc sine of flip and multiply, that'd be 2/3, so that'd be 1/2 minus arc sine of 0. And now we can actually evaluate these things. Arc sine, this is asking you to find the angle where sine is 1/2, so that's pi over 6. This is saying find the angle where sine is 0, that's 0. So our answer is just pi over 6. Pretty complicated problem. Pretty complicated problem, especially the stuff at the beginning. But who knows? I mean, I don't mind showing you this. Would I expect you to be able to do it on a homework set? Probably, looking at your notes. Would I expect you to be able to do it on the group portion? Maybe. Would I expect you to be able to do it on the individual? Pretty unlikely. Pretty unlikely. It's pretty tough for that. But AP people are they have a different view. All right, so we look at this thing. Let's try this one. So let's go through some of our methods. As I look at this, I see there's an x on the bottom and an x on the top, so I'm going to try my u du. So let's try this with a u substitution, x squared plus 1. So du would be 2x dx. Does that work? No, I've got too much on the top, so that's no good. And if I go the other way, let's say I took this as my u, I would get 2x plus 1, which isn't that either. So u du isn't going to work. What else could we do? What if we tried to separate? That was one of the moves that we learned earlier. Try to break each one of these up into their own. So that would be the integral of x squared over x squared plus 1 plus x over x squared plus 1 plus 1 over x squared plus 1 dx. I like this. That's one of those trig rules. I could look it up. I think it's arctangent. I like this. I could do a u du on that like we just did up here. I needed a 2x. I've got an x. I could then generate the term. But this one's bad news. So I like this part. I could do that. I like this part. I could do that. I don't like this part. I couldn't do that. Sad face there. So we're in trouble here. We don't have any moves so far. What was another move, though, that we did where we had a fraction over a fraction? Hopefully your math voice is saying long division or synthetic division. Now, synthetic division won't work here, but hopefully your math voice was at least thinking some sort of division. So as I look at this, I try to divide. So I'm going to take, this is my inside of the house, this is my outside of the house. Now remember, you have to account, it won't matter in this case, but you do have to account for every term, even the ones that aren't written. So x squared plus 0x plus 1, and then x squared plus x plus 1. And now we start to do some long division. X squared into x squared goes once. 1 times x squared is x squared. 1 times 0x is 0x. 1 times 1 is 1. Then I'm going to draw the line and switch the signs, negative, negative, negative. So x squared minus x squared is 0. X plus negative x is still x. And then 1 minus 1 is 0. So my remainder ends up being 0. So now I can rewrite this function. And I can't go again, by the way, because x squared has a higher degree than my remainder. So I now have the function 1. Actually, I'll go back up here and rewrite this. Remember how this works. That remainder then comes up here, and it becomes plus x over your divisor, x squared plus 1. Now that piece all of a sudden becomes like this piece and one that I can do a u du on. So my function changes into 1 plus x over x squared plus 1 dx. I'm going to give you a second. I'm going to encourage you to pause and try to integrate this. So here's how I did it. I split it up first. So the integral of 1 dx plus the integral of x over x squared plus 1 dx. And the reason I did that is because I'm going to have to do a u du on this, but I'm not going to have to do it here. And I don't want to get confused when I integrate with u's and with x's. So this is integrating according to x, so that's just going to be x plus. This is a little bit more work, so I'm going to leave myself a little note that u is equal to x squared plus 1. So du is equal to 2x dx. So let's see what I have here. I've got the x, I've got the dx, but I need a 2. So if I want a 2 there, I have to correct that with a 1/2 there. Times my x squared plus 1 is my u, but that's on the bottom. That all rolled into my du. So I have 1 over x squared plus 1, or 1 over u, which then I can integrate into the natural log of absolute of u, which is x squared plus 1, then plus c. So I could clean it up a little bit. Actually, I don't even need those absolute values, do I? I did here. I like to write them the first time just to show that I remember them. But why don't I need them there? That thing's going to end up being positive. So no matter what, that ends up being positive. Okay, let's try the same thing here. I'm going to give you a chance to pause and try to get ahead of me. See if you can figure it out. So we're going to start off right off the bat with some long division. I can't do synthetic. You can only do synthetic if you have a linear term. I actually think you can only do it if you have a linear term with a no fractions either. I never can do it with fractions. Leading coefficient has to be 1. Otherwise, there's some factors that don't show up. Anyway, okay, what does it take to turn x squared into x cubed? I need an x. I take that x and I multiply it, so that's x cubed. That's 0x squared. That's a 3x. Draw the line, switch the signs. So that's 0. That's negative 3x squared. 4 take away 3 is x, and then the 9 drops. What does it take to turn x squared into negative 3x? I need a negative 3. So then I distribute again. Negative x plus 0x minus 9. Draw the line, switch the signs. Ooh, that's nice. That's gone. That's x, and that's gone. So then when I rewrite my integral, this is really the integral of x minus 3 plus x over my divisor, which is x squared plus 3 dx. Okay, I'm going to try to integrate this fairly quickly. I would encourage you to pause and try to integrate it on your own by breaking it up and doing UDUs. So the integral of x is x squared over 2. The integral of 3 is 3x. And then the integral of this needs a UDU on it. So I'm going to say u is x squared plus 3. So du is 2x dx. So that means that I need a factor of 2, which I need to correct to make it 1/2. X squared plus 3 is my u. That's on the bottom, so that's natural log of absolute. This time I'm not going to write it because x squared plus 3 will always be positive plus c. Very doable. It's a very, very reasonable question that they would ask you on the multiple choice section. So we already did some of this. This is the idea of who do I pick as my u and my du. And then these two at the end, they're fairly nasty. I'm going to put them in my video right now, but I don't know how likely I would expect you to be able to remember them. But these first two you should do on your own. So I would encourage you to pause, do one, and then unpause to see if you did it right, and then try the next one on your own. So this is a situation where I can pick, in this case, I could pick either one to be my u, because what's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine, but either way, they're related to each other. I'm going to pick the one that doesn't need any negatives, so I'm going to choose my u to be sine of x. Thus, my du would become cosine of x dx. Now I can just jump right to this. I'll write this one out. I haven't written one out in a long time. So this, no, I'm not going to write it out. This is too easy. This all becomes du. There's u. My base just got attacked. So I'm going to integrate u. That would become u squared. So that would become sine squared x. U squared over 2 plus c. try the next one. If you haven't tried it on your own yet, pause and try it. This is very doable. So my inside function is sine. Maybe I'll write this one out the whole way. So that means I'm going to rewrite this now at the x and the dx all came together to make my du. The cosine and the dx came together to make my du, no problem. The sine's getting squared, so that becomes u squared. What's the integral of u squared is u cubed over 3 plus c. And then I've got to put my u back in there, so this would be sine cubed x over 3 plus c. All right, so the next two are identities that I didn't even know existed. And so I don't know how to say that. Oh, no. The next one's not too bad. We could do this one. No, we couldn't. No, we couldn't. So these both involve identities that I had not seen before. So I'll just throw it out there. Like I said, I probably wouldn't teach this in class, but I'll put it out there. Here's the note. That sine squared. Well, let me just throw out there why this doesn't work very well. Who's my inside function? Sine. So who's the derivative of sine, cosine? And I have no cosine. So the only way you'd be able to do this is if you knew that these trig identities were out there. Sine squared equals this mess. Cosine squared is equal to this mess. So in this case, we have obviously sine squared, so I'm going to use the sine squared formula. Let's use this color. I just used yellow. How about I can't decide. How about a nice blue? So I'm going to rewrite this now as the integral of sine squared. I'm going to use this formula. 1/2 times the quantity 1 minus cosine of 2x dx. Now this is very doable. So I would encourage you to pause and try to integrate this on your own. Let's see how you did. I'm going to take the 1/2 out. Yeah, I guess so. 1/2 integral of 1 dx minus 1/2 integral of cosine of 2x dx. So this one's pretty easy. 1/2, the integral of 1 is x. Now there's a plus c here, but remember we did that earlier example where you have multiple plus c's, so I can just throw the plus c at the end. Minus 1/2. Okay, my u my inside function is 2x. So my u is going to be 2x. That means my du is a 2, which means I need another 1/2. Integrate cosine. Integral of cosine is sine of u. And then I can put my plus c here. Maybe we clean it up a little bit. X over 2 minus sine of 2x over 4 plus c. So the last one, part D there, we're in a similar boat. I'm going to try to use one of these identities, but these are only for squareds. So think about what you could do with sine cubed to try to get it so that we could use one of these identities. Hopefully you came up with that you could split it up into a sine and a... So I can break this into the integral of sine of x, sine squared of x dx, and now I can use one of those substitution moves. So then I would integrate sine of x, look up here. Oh, no. Could I do it? No, yeah. I was going to say I could do... Oh, yeah, that's what I'm going to... Actually, this one isn't too bad. Try this one without... Think about what else we know about sine squared. I noticed that with the example, the way I did it. You do know how to do this without these messy formulas. This one's doable. This one's doable. Yeah. Think about what you know about sine squared and then try it from there. All right, let's see how you did. So one of the things that you should think of with sine squared is that sine squared plus cosine squared equals 1. That's a standard. That's a biggie. And you should be able to manipulate that however you need for whichever your situation is. In this situation, I have sine squared and I don't want it to be sine squared anymore. So I'm going to take sine squared, I'm going to rewrite it, I'm going to manipulate, I'm going to move the cosine to the other side. So I have sine squared would be equal to 1 minus cosine squared. Now what does your math voice say? I can't u to u yet. I can't u to u yet because I don't think I can u to u yet. Maybe I could have done this with a u to u at this point. Make that u. Derivative of that would be that. That would roll into there. I wonder. I'm going to do this with distribution, though. So now I'm going to distribute this sign. So that's the integral of sine of x minus cosine squared of x sine of x. I was thinking of the dx already. Dx. And now I can split these up and integrate them separately. So what's the integral of sine? That's negative cosine. What's the integral? Okay, so this is a u du. So I'm going to let u equal cosine because that's inside of the squared. So du would equal negative sine dx. So then I could take that negative. I've already got the negative, so actually I'm good to go there. So I'm really integrating u squared. So u squared would be u cubed x over 3 plus c. I wonder what would have happened if I let u equal, I do have enough room, so I'm been here for hours, and I'm still going to check it out because it's interesting. So let's go back to the integral of sine of x of 1 minus cosine squared of x dx. I'm going to let u equal cosine of x. So du would equal negative sine of x dx. So now I can rewrite this. Okay, I need a sine of x and a dx. I've got those two. Check, check, but I need to account for a negative. And then I can rewrite this as 1 minus u squared du. So now let's integrate this. This would be negative. The integral of 1 is u here, not x, because we're integrating according to u. Minus, add 1 to the exponent and divide. Oh, this is fun. I was going to say, wait a minute, it messed up. But no, that negative and that negative cancel each other out. So I get negative, what did we say u was? Cosine. Plus, what did we say u was? Cosine cubed x over 3. Hey, that's cool. Two ways to do that one. Me likey. All right, the last one, the last section, or not is it? No, it's not, is it? No, we got a ways to go here. So here's a simple one. It's confidence booster. Go ahead, you try it on your own. See if you can do it. I'm not exactly sure why I even put it in here. So let's see how it went. My inside function, u, is 2x minus 1. So du would be 2 dx. I look up, what do I have? So I need a 2 and a dx. I've got the dx, I need a 2, so I'm going to generate that with a 1/2. That's u to the 1/2 dx. Now this is something that I can integrate. So that would be 1/2 times add 1. 1/2 plus 1 would be 3/2. 2/3 plus c. And now we go back and clean it up and put our u back in there. So those 2's are gone. Our u is 2x minus 1 to the 3/2 over 3 plus c. That's definitely one you guys should be able to do at this point. So hopefully you did it on your own. Now these are a little sneaky. They're actually kind of fun when you see the trick. But all right, so let's start off. I'm going to do a u to u because I've got something inside of something else. So I'm going to start off with my u. It's 2x minus 1. And then we run into a roadblock pretty quickly. When I derive this, I get 2 dx. Now usually we don't have enough x's, but in this case we have too many x's in our actual function. We just want a 2. We don't want the x. Well, there's two ways to look at what u is. I can say u is 2x minus 1, but I could go the other way as well. So if u equals 2x minus 1, then therefore x must be equal to u plus 1 over 2. All I did was I resolved this thing, bump over the 1, and divide by 2. I now solved that thing for x. So let's go back to our function now and put all those pieces together. So I have the integral of x. Well, x now is u plus 1 over 2 times, what is this? We said 2x minus 1 was u to the square root is 1/2. And then I need a 2 dx. I've got the dx, so I've got to correct the 2 that I generated to get, what do you think? Now this still seems fairly nasty, but it's much more manageable, especially if you look at this section. What do you notice? These are something that these are like terms. I can distribute this and start to clean it up. So I have 1/2 times the integral of, actually, you know what? I'm going to change this to 1/4. Where am I getting 1/4? See that constant? That's also a constant. Now it's connected to this too because it's multiply. So I'm going to take that 1/2. I'm going to take it out front altogether. Then I'm going to do u to the 1/2 times u. That means I'm going to add those exponents. So that's u to the 3/2. Then u to the 1/2 times 1, which is u to the 1/2 dx. And now I'm going to start to integrate this. So this would be 1/2, 1/4, try again. 1/4 times the quantity. Okay, I'm going to add 1 to the exponent. So that would be 5/2. And then multiply by the reciprocal, or divide by 5/2, which flips it over. Plus add 1 to the exponent. So that's 3/2 over 2/3. And then what do you got to remember to put at the end? Plus c. Now, at this point, you can do two things. You can go ahead and put u back in there and then be done with it. If this is a free response, life is good. Most of the time, though, they'll want us to clean this up. How would you think about how you would factor this? Well, actually, I'm going to distribute at least the 1/4 and see if that makes life a little bit better for us. So this would become u to the 5/2 over 10 plus u to the 3/2 over 6 plus c. Now, if I said factor this, we haven't done one of these in a long time, but it's definitely doable. You would have to do a factor out least powers. Fulp? Maybe that's something I can start using as a name from here on out. Okay, so the least power. Actually, I'm going to take out these fractions too. I don't want to deal with them. So what's the least common multiple? What fraction could I take out that would kill both of those? So I'm going to go with 1/60th. No, I'm going to go with 1/30th. Would 1/30th work better? 1/30th. I'm also going to take out a u to the 3/2. What's that going to leave behind? So I took out 1/30th, so that's going to leave behind a 3. U to the, I took out 3/2, so that's going to leave behind 2/2, so that's just u. I took out 1/30th, so that's going to leave behind 5. I took out u to the, so that's going to leave behind, I took out u to the 3/2, so that's going to leave me with just that 5 there. Now I can go ahead and put those u's back in there. 1 over 30 times the quantity 2x minus 1 to the 3/2 times the quantity 3 times 2x minus 1 plus 5. Oops, plus 5. Math voice. Hopefully it says to distribute. So I've got 1 over 30. 2x minus 1 to the 3 halves times 6x, and then that's minus 3, so plus 2. Oh, geez. I can keep going again. Look. Ugh. This is divisible by 2, so I can factor out a 2 to cancel with this. So my best full credit answer would be something like this. 1 over 15, 2x minus 1 to the 3 halves times 3x plus 1. Boy, howdy. That's something else. Okay, let's have you try. Pause here. See how you can do with that same idea. Try it here. Okay, let's see how you did. I'm going to go with dark red. So I'm going to let u equal the inside function. So du is equal to 2 dx, which I don't have, which means I got to remember I got to generate that and then also correct for it. But when I derive this, I only want a 2, and I've got this x squared, so I'm going to rearrange this guy to try to solve it for x. So therefore x is equal to u plus 1 over 2. And now I'm going to take all that information and try to rewrite my integral. So I got to correct. I need a 2 and a dx. I've got the dx, so I'm going to correct that with the 2, 1/2. I need on my numerator, and the numerator I need x squared. So I'm going to take this thing and I'm going to square it right off the bat. So you should try to square this, square the numerator and square the denominator. See how you do. You should have gotten u squared plus 2u plus 1 over 4. Because u squared plus 1, you got to write it twice and then distribute. And then this is still getting multiplied. All that was the x squared piece, and I still have this piece, but that's on the bottom. So that's u to the, that's what we called u, to the negative 1/2 du. Now I want to try to, I got another constant. I'm taking that guy out right now. So that becomes 1/8 times the integral of, okay, so this is u to the negative 1/2 times u to the second. When we multiply like x to the second times x to the third, that becomes x to the fifth, so we're adding exponents. 2 plus negative 1/2, so that would be u to the 3 halves. Plus, remember, I only took out the 1/4, so I still have this 2. That's 1 plus negative 1/2 would be 1/2. Plus u to the negative 1/2 du. Now, I don't want to factor out least powers yet because I haven't integrated. So you still need to integrate. 1/8 times, okay, add 1 to the exponent, 5 halves, 2/5, plus 2 times, I've already got the 2 out there, u to the 3 halves, 2/3. Add 1 to the exponent, that's u to the 1/2, then 2 over 1, and plus c. Oh boy. I'm going to take that 8 and I'm going to put it back in so that it's easier for me. I mean, I guess I could see that I could take out a 15th here, but I want to see what this looks like if I try to clean it up a little bit. Maybe it's not as nasty as it looks. So I'm going to distribute the 1/8. So 1/8, that's going to leave me with u to the 5 halves over 20. Plus, that's going to be 4 over 8. That's going to leave a 2 on the bottom, so that's u to the 3 halves. Right, that's 4, that's 2, that's 6. Plus, then that's going to be u to the 1/2 over 4 plus c. And then that 1/8 gets times by the C, but remember, we don't even know what C is, so we don't really care what C is. So what is the least common multiple of all of these bad boys? 60? I think 60 is the best we can do. So 1 over 60 times, 1 over 60, u to the 1/2. So this is a scribble. U to the 1/2. Then that would leave me with u to the second. Try again. 3, because I divided out the 60, that's going to leave me with 3 still in there. Plus 10 u plus 15 plus 15 plus c. I'm not going to try to do any nicer than this. Besides, don't forget, you got to actually answer the problem. I probably should have stopped a while back. This is getting pretty nasty. 1 over 60 times the quantity 2x minus 1 to the 1/2 times the quantity 3 2x minus 1 squared plus 10 2x minus 1 plus 15 plus c. Whew. I do not want to try to clean that up any more than that. They wouldn't make you do something like that on the AP test either. Just take up too much time. And then finally, the last page of this marathon sort of, not a lot of fun mathematics, a lot of like nitty gritty stuff. Okay, so first one's not too bad. I'm going to encourage you to try to do that one on your own with this sort of double u to u substitution sort of moving back and forth thing. So pause and go get them. So let's see how you did. I would start off by identifying my inside function, which would be u equals x plus 1. So then du would equal dx. I've got a 2, so I've got to get that sucker out of there. That's no big deal, but I've still got an x left around. And I don't want an x. So I'm going to have to do a double move. So now I'm going to move the 1 to the other side. And let's rewrite our integral and see what we have now. So I'm going to take out that constant 2. The integral of, we said x was u minus 1 over, and then we said u was x plus 1 squared, so that's going to be u squared. And then du was dx, so there we go. I'm going to split this up now. I can divide these. I can separate. So this would be the same as, I'm going to write it over here. 2 times the integral of u over u squared is 1 over u minus 1 over u squared. I'm going to rewrite that as u to the negative 2 du. Notice why I did that. This one is not integrable when I write it as to the negative 1. That's going to remind me that it's natural log, where this one I can add 1 and go from there. So equals 2 natural log of absolute u, which is x plus 1. And then I'm going to add 1 to the exponent and then divide by that. So that's going to turn out to be positive. I'll write it above here. So this is going to be u to the negative 1 over negative 1 when I integrate it. So that's going to be 2 over x plus 1 plus c. So this was the negative. The negative made the negative positive. That's u to the negative 1, so I bumped it back to the bottom. And don't forget you're distributing that 2 to both of the pieces inside. Okay, so I'm going to talk about E and not D. And then, if you want to figure out D and E, I think these are both pretty extreme cases. But I want to do one example like that, and then I have it in there forever. I don't know if I'll actually teach this in class. So in this case, we tried about 50 different things. So if you look at my notes, when I tried to do it before, when I'm watching the video and he's joking around with the students, I tried it a bunch of different ways. and I ended up running into a stone wall. So the way that he figured it out, I don't know if he figured it out or if someone had to show him along the way. So he said, all right, I'm going to let just u be this messy little square root of 2x. Now, when I derive that, I get 1/2 of 2x to the negative 1/2 times 2, but that's not any better. That's not any better because I don't have an x to the negative 1/2 because I've already subbed out this piece. So what he did instead, he looked at u equals, and then he squared it right off the bat. So he said, okay, u squared then is going to be equal to 2x. Pretty sneaky, huh? Now I'm going to derive this. So what's the derivative of u to the 2x? That's 2u du. What's the derivative of 2x? That's 2 dx. And then he canceled out the 2's to find out that u du is equal to dx. So now we can rewrite this original integral as the integral of, what did we say dx is? Dx is u du over 1 plus, and then we already defined u as being the square root of 2x. So that's u. And now I can start to break this thing up. This is the integral of what's u over, oh, no, sorry. I want to do I got to do some division here. We can't, sorry, I was going to split it up, but there's two things on the bottom, so we can't split it up. So I got to do some long division. So I'm doing u is getting divided by, well, I'll pick a different color, maybe a nice pink. So I've got u that's getting divided by 1 plus u. I'm going to flip it around so it's in the right order. U goes into u once. 1 times u is u. 1 times 1 is 1. Draw the line, switch the signs, and I get 0, and I get negative 1. So this turns out to be, remember how we put this back up here with the denominator, or sorry, the divisor. So this turns out to be 1 plus, 1 minus 1 over u plus 1. Which is something that I can now integrate. So I can integrate 1. I'm doing it according to u. So the integral of 1 according to u is u minus, this is a u du problem. That's a simple one because u, actually we could call it even v or something like that. V is going to be equal to u plus 1. So dv would equal du. So in other words, I don't really even care because the derivative of this is going to be 1, so it's going to give me exactly what I had before. So this, what's the derivative of something over underneath 1? The natural log of absolute u plus 1 plus c. And then don't forget to actually go back and put your u values. Square root of 2x minus the natural log of absolute square root of 2x plus 1 plus c. So at the end of that, if you're looking at it and you're like going, what the heck just happened? Don't worry too much about that one. Like I said, I am more wanted in my notes permanently than to really make you go through and do it on your own. I think that's a pretty extreme. All the ones you're going to see, I can tell you right now, they're going to look like this. They're going to be linears, is when you have to do this reverse substitution. You're never going to have a UDU where it's pretty unlikely, pretty darn unlikely. All right, so this next section, I'm giving you some information and you're going to manipulate this until it starts to look like this. So you're going to mess around, you're going to try to figure out what U is, you're going to see if you can factor anything, because I want to integrate something that is really tough to integrate, but they gave me a hint. They told me this much is equal to this. So if I could get this thing to somehow look like this, I'd be on easy street. So let's point out two things. The first thing I want to point out is this, what style would you use? Hopefully you said UDU, because this is a UDU problem. My U would be x over 4. So then my DU would be 1/4 dx. So if I look at what I've got here, I'm going to write my integral symbol. I want to have 1/4 dx. I just have the dx, so I want to have 1/4. This is a little bit different than what we're used to. I want there to be a 1/4. So what's the correction for a 1/4? It's a 4. So I'm going to multiply by a 4. That gives me my du, the 1/4 that I created and then I corrected. What about these 3's? That's a problem because this is supposed to be 1 plus cosine. We don't want those 3's there, but they both have a 3. So I can factor out a 3, but where's that 3? It's going to be on the bottom. And then I can try to rewrite this whole thing. 1 over, so what do I have now? Those 3's are out of there, but that 1 is still alive. What? 3 divided by 3 is still 1. 3 divided, cosine of, and what did we say x over 4 was? U du. So this is 4/3 times, look, this, even though we switch the u to an x, that's fine. It's still going to give us the same values, except where there's an x, we're going to put a u. So this piece and this piece now look exactly the same except for the 4/3. So this is going to turn out to be tangent of, we said x. Over here, these are x's, but remember, r's are going to become u's. Well, I'll write it out with a u. How about that first? U over 2 plus c. And then now we can put our u in there, so we get 4/3 tangent. Okay, if u is x over 4, and I'm dividing that by 2, this is going to become x over 8 plus c. Let's have you, oh man, I hate it when I do that. Sorry about that. Let's have you try it. Let's see if you can finish this next one. Try to break up. How can you rewrite using u's? How can you rewrite that second integral? And let's see how you did. So I chose to take, I'm going to let u be 5x. So that means du is going to be 5 dx. So now I'm going to look back up here. I'm going to try to turn this into my u du stuff. So I've got the integral of from 0 until infinity. So I want to have, I always try to start by making my du first. So I need a 5 and a dx. I don't have a dx, so if I want to make a 5, I have to correct that 5. So there's my 1/5. I need to do something about this x. I'm going to want all this stuff to be in terms of u's. Well, actually, let's go to the denominator next. So this becomes e to the 5x. Well, we said 5x was u, so I got e to the u plus 1, and I said I already built the du. So look, we're close. We're close. We got e to the u plus 1 du instead of x's. But this is now an x. I don't want it to be an x. I need it to be a u. So I'm going to go back to this. What can we do with this to try to figure out something for x? Well, I can resolve this so that x is equal to u over 5. So if x is equal to u over 5, then I can put u over 5 in here. But it's still not right? It's supposed to just be the variable that we're talking about. So I'm going to take this u over 5, and I'm going to take out the 1/5 again. So we would get 1/25, the integral from 0 to infinity of u over e to the u plus 1 du. Now this mess looks like that mess, which means we can sub it out and put in what it's worth. This is worth pi squared over 12. 1 times pi squared is pi squared. 25 times 12, 300. I'm going to encourage you to try to do it again. You try it on your own here. See what you can do. See how far you can get. Now, feel free to pause again if you're starting to figure stuff out, but if you need a couple hints, start off by trying to, if you can do any UDUs. So I've got, this is my inside function. So u is 5x, therefore du is 5dx. So now I can rewrite this as the integral from, I didn't give myself enough room. So I can now rewrite this as the integral. I'm going to give myself some room. Let's try to build our du first. So our du is going to be, I need a 5, which I don't have. So I need to build the 5 inside, which means I need to correct it outside, 1/5. And then I'm going to look, all this stuff, the only thing that changes is going to be that guy. So that's going to be the natural log of a plus b cosine of u du. Well, life is good right here, except we've got these boundary things. And these boundaries go from 0 to pi over 5. And this trick only works if I go from 0 to pi. But remember, we changed our variable. We changed our variable from x to u. So now we need to also change our boundaries. This is still when it was x. We need to change our boundaries to what they would be if we're talking about u. So if x is 0, what's 5 times 0? Obviously 0. But if x is pi over 5 and I times that by 5, that lands me at pi. So now I get 1/5 times this whole mess now is this whole mess, which is 2 pi natural log of 2. Oh boy, how would you clean that up? I probably would stop here. 2 pi over 5 natural log of 2. That's where I would leave it. My guess is they would take that 2 and bump it up to the exponent. So maybe you'd have something like this, pi times the natural log of 4 over 5. Or maybe they'd get real crazy and bump that whole thing up to the exponent altogether. So it's the natural log of 4 to the pi over 5. Which then we could clean up again. And remember, that's the root and that's the power. So this could be the natural log of the 5th root of 4 to the pi. Oh, man, that'd be nasty. Just being a jerk at that point. Just being mean. I don't know, but that one I think is doable. That one's crazy. The last page, the last idea of this section. So integration of odd and even functions. Remember, an even function is a function that has symmetry across the y-axis. This is an example of an even function, symmetrical across the y. This is an example of an odd function. It has symmetry, but it's symmetry rotation. This has reflective symmetry across the y-axis. Odd functions have rotational symmetry around the origin. So this little theorem makes sense here. If you think about it, if you have an even function and you're going from negative a to a, why does it make sense that that's the same as twice the area under the curve from 0 to a? Because this is going to be exactly the same as this distance, right? They're always going to undo each other. However far out you go to the left, it's going to be exactly the same as however far you go out to the right. So if I figure this out, I can just add those two results together or double it. And then the same argument would happen here if we're talking about an odd function and we're going from negative a to a, you're always going to end up at 0. Because no matter how far you go to the left and then how far you go to the right, one of those is going to be above the x-axis. The other one's going to be below the x-axis. It's going to be exactly the same areas. One's going to be positive, one's going to be negative. Okay, so I need to first, if I want to use one of these tricks, I have to first figure out if my function's odd or even. So let's go through and remember how we do this. It might have been a while, but you check oddness and evenness by plugging in a negative x. So in other words, I would say, what is sine of negative x? How do I want to do this? Negative 3 to 3. No, I'm not ready for that. I'm just checking for oddness and evenness. Sine of negative x. So this one's a little tricky. This one you can't just tell by looking. You got to think about it a little bit. So if I'm in the unit circle and I go to some angle like 45, and I go to its exact opposite angle like negative 45, what happens to those y values? One's above and one's below, but they're the same value. So this little piece here is an odd section. That section's odd. So then I check to see if this is odd. I plug in negative x. Negative x cubed is negative x. So I'm sorry, I didn't explain that very well. An odd function, an even function, f of negative x is equal to f of x. So if I go over here to negative 2, I'd go up to 4. If I go over here to positive 2, I would go up to 4. An odd function, I'm going to do the same thing with a negative. So now when I go over to, let's say, 2, and it takes me up to 7, when I go to negative 2, where does it take me? Down to negative 7. In other words, it changes the sign. So when I put in a negative x into sine of x, I got out an answer that was the exact opposite of the original value. So sine of 45 is exactly the opposite of sine of negative 45. Negative x cubed is negative x to the third. So the function stayed the same except for the sign. So this is an odd function. And then the same argument here, this is going to become negative x over negative x squared plus 1. Well, negative x squared, this is going to stay as negative x. So this is going to become negative x squared becomes x squared plus 1. What changed between these two? They're exactly the same except one is negative. So this is also odd. So if you have 3 odd functions added together, you have an odd function overall. So the answer to this is a big fat 0. Now I know we did a lot of work here, but most of the time you wouldn't have to prove all this. You could just kind of look. This is supposed to be a time saver. Now I'm explaining every little detail, but you wouldn't have to explain all those details going forward. So let's have you try the next one. See if you can figure out the shortcut here. Okay, so I put in 1. I put in a negative. Well, there's nothing to plug a negative into, so did this function stay the same? Yes, that's an even piece. Put a negative into here. What's a negative squared? A positive. So that function would stay the same. Cosine, let's go back to our little picture over here. Here's my positive 45. Here's my negative 45. What do you notice about their cosines? Their x values. They're the same. So whether you go odd or even, or whether you go positive or negative, you're even again. So this is the same as 2 times the integral from 0 to pi of 1 plus x squared plus cosine of x dx. Now, when I first looked at this, I argued, what's the difference, right? I'm going to have to integrate and plug something in anyway. So you could make the argument that there's not that big of a difference, but we'll see. Okay, so 2, go ahead, try to integrate this on your own. Pause if you haven't. X plus x cubed. Okay, the integral of cosine, so derivative, sine's derivative is cosine, so that's just sine. That's nice, no negatives. From 0 to pi. Now I can start to plug and chug, so this is going to be 2 times. I got to put pi in there first, so that's pi plus pi cubed over 3 plus sine of pi, so go over to pi. What's your sign there is 0. Minus, put in 0. What's sine of 0? 0. So this actually wasn't too bad. So 2 pi plus 2 pi cubed over 3. And then the last, you can tell pretty quickly that this isn't going to be odd or even altogether. So we can go by each one. When I put a negative into this, it's going to stay negative, so that's odd. When I put a negative, this is going to come out to be even. This is going to be odd. This one's going to be even. This one's going to be odd. This one's going to be even. Now, this is a problem, yet again, I would argue it probably wouldn't be too bad to just actually do. But Corpy shows a nice trick here, which I kind of liked. He grouped it into 2 separate integrals. He did the integral from negative 1 to 1 of 5x to the 5th plus 11x cubed minus 15x dx plus the integral from negative 1 to 1 of x to the 4th plus x squared plus 1 dx. And why did that make a lot of sense? If these are all odd, so when I put them together, this section becomes odd. So when I integrate this, it becomes a big fat 0. Where the other part, I can integrate this fairly quickly. X to the 5th over 5 plus x to the 3rd over 3 plus x from -1 to 1. Now we can start to clean this thing up. So that would be what? 1/5. Oh, crap. I forgot the 2 out in front. Right? This has to, because, oh no, I'm going from -1 to 1. I'm okay. I guess I should have made that a 0 so that it doubles out, but I didn't. So we're going to have to live with that fact for the rest of our lives. So now I can plug 1 into here. So this is going to be 1/5 plus plug 1 in, that's 1/3 plus 1 minus plug in -1, so that's -1/5. Plug in -1, so that's -1/3. Plug in -1, so that's -1. I'm subtracting, so life actually, so I'm going to do, this is going to be 2/5. 3 minus a negative would be 2/3. 1 minus that would be 2. Oh, common denominator at this point. I guess 15, so I guess that's not too bad. So 6/15, dang it, sorry. 6/15 plus 10/15 plus 30/15. 30, 40, 46 over 15. Marathon. Now, hopefully you didn't wait until this point to start doing homework, because you got an overwhelming task at this point, so you probably will chicken out and not do it. But this should be able to get us to a spot where you should be able to finish most of it. Now, most of these are tricks. A lot of these tricks you don't need in the homework. Most of the homework, it seemed to me, was pretty straightforward with u to u substitutions.